Welcome everyone to lesson 1.8 of Precalculus, which is all about rational functions and zeros. Last time we talked about end behavior. This time we're going to be talking about what happens in the middle of a rational function. So let's get started. So let's remember what a zero is. A zero is an input that makes the output of a function zero. So for a rational function, a zero would be what makes the numerator zero, but does not make the denominator zero, because if it makes the denominator zero, it's no longer in our domain. So let's look at question 1. So question 1 says, use the function below to answer the following. So we have f of x here, and I have a very crude drawing of what f of x looks like. So we can see from the diagram that, let me get a good marker here, that our zeros would be x equals -4 and x equals +2. So let's look at the function and see how we can find this analytically. So if we look at the function itself, I can factor I can factor the numerator definitely. I would get x plus 4 and x minus 2, which explains where the -4 and the +2 come from. But the denominator is quite weird. If I were to try to factor this, I would get 2x squared plus 2. Well, if I think about it, the 2 doesn't really matter. We're really going to focus on this part here. If I take a real number and I square it, the lowest thing I'm going to get is 0. And if I add 2 to it, that means it's never going to be 0. The lowest thing that's going to output is 2. So the domain of this function is actually everything, because there's no input that would make our denominator 0 in the real number system. If I were to solve it, I believe I would get plus or minus the square root of 2i. So a little bit weird. Imaginary numbers, fun stuff. Zeros are going to be where we factored our numerator, and they're going to be a -4 and a +2. And I can check that they work and they're actually zeros by, if I wanted to, plugging them into the denominator and seeing that I do not get a 0 out from them. So depending on what you're being asked, that might be a little bit of a shortcut for you. But I like to focus on the denominator first, typically, to figure out what my domain is. So that way, if I get that from the numerator, I know that it's definitely not a 0. So that's all fine and dandy. And that's the big idea of today, is what are zeros? But there are two weird things that could happen when something makes the numerator and or denominator 0. So if it just makes the numerator 0, it's a 0. Fun. If it makes both 0, we get a whole. And I'll explain this in more detail later. But for now, you can think of a hole as we are taking a hole punch and punching out a hole in a function. So it looks normal, except for you just have a random hole in one spot. So there's a technical definition there. Let's look at this function and see what's going on here. So I notice first off the bat that the numerator is factorable. And if I factor it, I get x minus 4 times x plus 3. So if I notice, I get this x minus 4 in both, right? And that would cancel, right? So I could cancel that out and cancel that out. That leaves me with x plus 3. So this function is going to behave like x plus 3. But there's a catch. 4, which made the numerator 0 and the denominator 0 to begin with, isn't actually in the domain. So our domain is everything but 4. So -infinity to 4, and then 4 to infinity. Our whole is going to happen at this 4. So this is going to happen at x equals 4. For now, we're not really worried about what the y value of the whole is going to be per se, but if you can cancel it out like this and it goes away completely, it's a whole. So g of x is equivalent to x plus 3, except we cannot have 4. So it's equal to x plus 3, except for when x is 4. So when is that 0? Well, that would be 0 at -3. So at 1, 2, 3, -3, we would have a 0. Let me get a nicer marker for that. Oh, I didn't pick it apparently. There we are. So we're going to get a 0 at -3. And then we're going to follow this function. It has a slope of 1, so up 1, to the right 1, over and over and over again. And it actually goes off the graph for me, but poor planning on my part. 1, 2, 3, 4. So there would be a hole here, but it would follow this function's behavior normally, except there would just be a random hole where the x was 4. So it looks like a line, except we got a little hole missing from it somewhere. The other weirdness, so if they have it in common with both the numerator and denominator, it's a hole. If it's only in the denominator, if it only makes the denominator 0 and not the numerator, it's a vertical asymptote. So that is that weird behavior we saw last lesson that we kind of didn't really go over too much in the video. Hopefully you asked lots of questions about it in class. But these vertical asymptotes make these beautiful distortions of our graphs. And they're quite nice to see. So they only occur when the denominator is exclusively 0 and not the numerator. So let's factor this out and see what's going on. So the numerator is factorable, so let's factor out the 4, x plus 2. And the denominator is also factorable, x plus 5, x minus 2. So the -2 is a 0, but -5 and +2 are not the domain. So domain -infinity to -5, -5 to 2, and then 2 to infinity. Our hole, well, we don't have any holes here. We don't have any common zeros here. We got a -2, a -5, and +2. None of those overlap, so we don't have any. Zeros, we actually had a 0. We had a -2. We can see that graphically right here. And our vertical asymptotes are x equals -5 and x equals +2. So we can see that graphically through these weird distortions. And they could be going in the same direction depending on the behavior of the graph, right? But analytically, they are values that make the function's denominator 0, but not the numerator. So let's combine all of that in this function here. So we're going to see if there's holes, zeros, what the domain is, the vertical asymptotes, horizontal asymptotes, y-intercept, the whole kit and caboodle here. So let's factor the crap out of this. So we'll get x minus 3 times x plus 3. We will have x minus 3 and x plus 1. Oh, that was a little weird. So we get 3, -3, 3, and -1. So first off, we can kind of tell there's two values that aren't in our domain. Let's go ahead and list them. We do not have -1, so -infinity to -1. We do not have 3, so -1 to 3. And then we'll finish it up going 3 to infinity. Holes. We do have a common 0 for the numerator and denominator at 3, so that would be our hole. Our 0, what makes the numerator exclusively 0, that would be -3. Vertical asymptotes, what makes our denominator exclusively 0, that would be -1. Horizontal asymptotes, we talked about this last time. So this one has the same degree in the numerator and denominator, so we're going to take the ratio, the leading coefficients. 1 over 1 is 1, so that would be y equals 1. And something we didn't talk about last time, the y-intercept. If we remember from the very beginning, or maybe from past classes, y-intercept, instead of the output being 0, the input is 0, which means all of our terms that contain an x become 0. So that leaves us with a -9 in the numerator and a -3 in the denominator. That looks awful. And a -3 in the denominator, and that reduces to a +3. So the point would be 0, 3. Hopefully that's not too bad. So analytically, not awful. Factoring is the worst part. Let's look at it analytically. No, not analytically. Let's look at it graphically. Losing my mind. So domain, I see we have a vertical asymptote here. And we have a hole at positive 7. So that would be negative 4, so negative infinity to negative 4, negative 4 to 7, and then 7 to infinity. We do have a hole, x equals 7. We have a 0. We have a couple, actually. We have one right here and right here. So we have one at negative 2 and positive 2. Vertical asymptote, we only have one of those. X equals negative 4. Horizontal asymptote, this one doesn't have any. It has that infinite end behavior. Y-intercept, it looks like we're crossing somewhere between 0 and negative 1, so make your best guess. We'll go with negative 1/3 just for kicks and giggles. So, a sign chart. So, you may be asked when a function is greater than or less than 0, like we were with polynomials. So let's build this with rational functions in mind. So the x values we're going to use is we're going to include all of these numbers that we can. So we're going to go negative infinity to negative 2, or negative 4, my bad. We're going to look at negative 4. We're going to go negative 4 to negative 2. See what happens at negative 2. Negative 2 to 2. See what happens at 2. 2 to 7. See what happens at 7. And then we're going to go from 7 to infinity and see what happens there. Lots of different things to look at. We've already done a lot of this. What happens at 4? We have a vertical asymptote there. It does not exist. Does not exist. What happens at negative 2? It's a 0. We're going to put a vertical asymptote there, by the way. What happens at 2? It's a 0. What happens at 7? It's a hole. It does not exist, but it's a hole. The others we can actually tell just by looking at the graph. What happened before negative 4? It was below the x-axis, so it was negative. What happened between negative 4 and negative 2? Negative 4 to negative 2 was above. That was positive. Negative 2 to positive 2 was below, so that's negative. 2 to 7 was positive, and 7 onwards was positive. So what happened here? When did the signs change? Well, they changed with a vertical asymptote. They changed with a 0. We knew that they would with polynomials, right? Or that they could with polynomials. But they didn't change with a hole, which makes sense. It's just a stamp out instead of weird distorted behavior. So when you are solving, when is f of x greater than or equal to 0 for rational functions, you look for the zeros and you look for the vertical asymptotes, but you don't need to find the holes. The holes don't matter for this one. Now do keep in mind that the signs don't have to switch between zeros. Remember, we had multiplicities of 2. The same thing happens with vertical asymptotes. If vertical asymptotes have a multiplicity of 2, it's not going to change as well. And we'll talk about multiplicities with all of this stuff a little bit later, but just keeping your mind open and fresh to these ideas. That is it for lesson 8. If you have any questions, make sure you ask them in class. Otherwise, I'll see you in the next lesson.